So we are going to have Henning Meyer, and he will be talking to us about Heap snapshot analysis for C++. Henning is not sharing any fun facts, so we need to work on that. But he is a software developer with PhD in algebraic geometry and 12 years of professional experience in high performance and real-time computing in C++. He's also currently working with a legacy enterprise application, and that inspired him to work on some debugging tools for C++. So, Henning, the stage is yours.
Okay, so a brief introduction of myself as far as it is relevant to this talk. At my first job, we hired people straight from university, no industry experience. Software was very buggy and also very hard to debug. We need to learn about obscure debugger commands like keeping threads running while debugging, otherwise the hardware driver would kill our application. And when we had to debug, because the entire company was made up of researchers, we treated debugging as a research problem. And that is in big contrast to my last job, where everyone has been working on the same problems for 10 years, and they are using their IDE, and they hit run in debug builds, and their IDE stops, and that line needs to be the cause of the problem. Then they fix it. And if it doesn't solve the problem, then they move on to the next problem because there's hundreds of bugs. And with my previous experience, I always got asked to work on the hard to debug problems, and we only have a core dump, when we cannot reproduce it, when we need to analyze memory consumption or memory corruption. And this created a really bad feedback loop where I would spend more time debugging and get more experience in debugging and end up spending all my time debugging instead of writing software. And that is what made me realize I want to automate this. I don't want to spend my time personally debugging. It's not valuable to me. It's not valuable to the company. We need to write better debuggers. And the best way to not spend time on debugging is to invest in quality beforehand. So I'll be talking about smarter debuggers, but really what you should do is write more tests, do more code reviews, use sanitizers, use static analyzers. Debugging should be your last resort, and effort spent on preventing bugs really pays off compared to having to debug. And I make a distinction between routine debugging and research debugging. Routine debugging is the problems you can solve easily with your IDE, the problems that non-experts can solve. If you come to C++ from Java, then the debugging experience is exactly the same. You hit run in your IDE, you get a stack trace, you look at the line that the debugger is stopped in, and in C++, we have a lot of problems where this doesn't help us. because there is no line that you can stop in if you have to debug a memory leak. There is the line that your program crashes might not be the cause of the crash. It might be entirely unrelated. And the things that make a problem easy to debug is it needs to be easy to reproduce, and it needs to be easy to analyze. So a null pointer dereference would be the example, or an integer divide by 0. Your debugger will do the right thing and point you exactly at the problem. And the problem is that we have lots of other problems that we need to debug. So if we use uninitialized data, the behavior might change every time we run. The behavior might also change every time we build. And if you have a race condition and you insert a print statement to analyze it, you change the timing behavior. And the hardest problems are those where all you have is a core dump and you need to analyze a memory leak, or you need to analyze memory corruption where you only see the symptom of a corrupted data structure and you need to reverse the chain to get to the cause. And I do this by hand, manually. I've learned how to do that. It's very time consuming, and it's not necessary that I debug these problems by hand. So some of these problems can be done just the same. You hit analyze in your IDE and it points you to the problem. This is where I want to get, that we can move more problems into just click on analyze and anyone can debug it. And the way that I do this is I do snapshot analysis, which is a snapshot of the currently running program, or usually a core dump. And I look deep inside into the core dump because it is full of information and it's currently not accessible. So if we take a step back and look at this at a higher level of abstraction, then we have our programs. And if you do this as a research problem, then I think of programs as a library of functions. Our debug information is a library of types. And a core dump is a library of objects. And the difference is that we can use a program as a database of functions. There are tools to read them. We have tools to read debug information, but we don't have tools that find objects deep inside the heap in a core dump. And I'm saying we can write these tools. We can have these tools. And if we want to write a tool that finds objects that we have allocated that are contained inside containers, then we need to find objects on the heap. And the only way to find objects on the heap in a C program is to follow pointers. But the problem is that pointers don't have to point at a valid object. Pointers are allowed to point at the end of an array. We don't know whether a pointer points at an object or at the end of an object. But pointers are also the only way to find things. So this is very ambiguous and hard to do for an automated program. And it is similar in C++. Our memory is managed by smart pointers and by containers, but internally they contain pointers. And we also have iterators, but we have the same problem with iterators. If I have an iterator, I don't know whether it points to a valid object or not. And the one difference we have in C++ is that references have to refer to a valid object. But we have our strong types. We have classes that maintain their invariants, and I can't use iterators that I find in the program, but I can use the begin and end methods of a container to generate valid iterators. And I can use these iterators to get pointers that I know are good to find objects in a running program. And so this is the algorithm that I use to find objects in a running program or in a core dump. I ignore all existing pointers and iterators. I look at the local and global variables. And if from type information that I get from debug information, I know that this is a container that has begin and end methods. I emulate the instructions in the begin and end methods, and that tells me how to get iterators. And the iterators have a dereference operator that gives me a reference, and that is how I find objects. And it also has an post-increment operator, a pre-increment operator that I can use to get more iterators. And that is how I want to find all objects in a container. And I have a live demo for that. So I'm running compiler Explorer locally on my machine, and I have written a custom tool which runs the program in GDB to generate a core dump, and then I run my analysis on the core dump, and I have just declared a local variable, and now my program finds one vector of a list of the findMe class, and it's an empty vector. And then I fill the vector with an empty list. And then I put an object into that list. So now my program contains a vector, a list, and the find me class, and my analysis program does not find it because it relies on the begin and end methods, and they are not instantiated. So I need to add some code that calls begin and end. And I do that in this exercise function, which checks that I have begin and end. And if it does, it uses a ranged for loop. And a ranged for loop behind the scenes will exercise all the methods I need. It calls begin, it calls end, it calls dereference on the operators, and it calls advance and compare on the iterators. And now my program finds a lot more things. It's actually hard to read because I also find allocators and other things, and I have a somewhat nicer way to look at this. So we have a vector of a list of find me, and I would like to point out that a lot of effort goes into saying that this is a vector of a list, because behind the scenes this is a vector of a list of find me, but the list also has an allocator argument, and the vector also has an allocator argument. And debug information actually contains the fact that the template argument is defaulted, so a debugger can actually hide the defaulted template arguments and can show you a simplified version of the type name that is a lot shorter than what you get by demangling the full type name. And we have a lot of things on the heap that includes the find me class that I showed you, and this class has a label which is a string, and there's the definition. And my tool does not have hard-coded pretty printers for a string, unlike current debugger, so it doesn't know how to display a string. But a string is also just a container of characters. And if I add code to my program that calls begin and end on a string, then yeah, it doesn't work. Why does it not work? Then I can now print the contents of the string without having to hard code this. And so I think this is one utility by being able for a debugger to dynamically analyze the type system, that we don't have to write pretty printers by hand. So if you have a large code base with thousands of types, generating pretty printers on the fly is one use case. But finding all objects in a running program or in a code dump has a lot more uses, because we can use this information to look for problems and to look for problems proactively. So as I said, I go through a container, I find all iterators, so I know what the valid iterators are, and I can tell what the invalid iterators are. So for this simple program, we have a vector, then we get the iterator, then we call a function that invalidates the iterator, and then we use the iterator. And this will not be caught even if you run a hardened implementation that will check out of bound accesses, because the iterator doesn't carry bounds information. And we can, if we put in the effort to diagnose these common problems, we can, before we run line 13 in a debugger, when we step through it, we can diagnose that this is a line that will cause undefined behavior. And current debuggers don't generate warnings or errors. Our compilers generate warnings and errors. We have static analyzers that generate warnings and errors. And I think there's a gap in our tooling that our debuggers don't run any diagnosis paths and don't generate warnings and errors. They don't check for ODR violations, which they can. It's hard to do, but it's worth the effort. And I just talked about how I do this with containers. And I look at the public interface, and it works the same for smart pointers. They have a public interface, the conversion to bool, and the dereference operator. And optional and expected also have a public interface that I can use to find this type behaves just like an optional, even if it is a custom implementation, like optional light. And so for many types, we can just write an analysis path that works purely on the public interface. And it doesn't work for std function because there's no public interface to get the value out. If we want to find all objects in a C++ application, then I still need to write some hard-coded handling for some types, but it's only std function and std variant and std any. Somewhat in between, probably need to hard code this, but I think it is feasible for a pure C++ application to have handling for all containers and to find all contained objects, and then you can run queries on them, like what is the largest vector? Are there any containers with more than 100 elements? Are there any containers with more than 100 elements by following them by counting owned elements as well? So this will give you a lot of information about the memory consumption and a lot of information about the internal state of your program that is not accessible with current tools. And this is analyzing one point of time. And if you look at time travel debugging, you can switch at the point of time that you are looking at. And if you can write a function that detects a problem in your code, for example, you say for every std vector, I want to check the internal pointers. Do they point to valid memory? And then you can use a bisection on the timeline in your time travel recording to find the first point in time where the problem happens. And we currently don't have good tooling for time travel debugging. It's a good tool for experts that know where to set the hardware watches and what to look into. But I think if we get a lot more understanding for program state, then we can have recipes for how to debug with time travel debugging that we can hand off to tools or to LLMs, and we can automate the time-consuming parts of debugging. And there's a second part of problems. We have memory leaks. And if I have a memory leak, then all the methods that I talked about don't help, because the current program does not have a pointer to the leaked objects. We cannot discover them. We don't know their type. But it's still a problem. It's not a security problem. It can't be used for an exploit, but it's a functional safety program. I get annoyed if the program crashes because it runs out of memory. And current tools are very good at telling you you have a memory leak, but it cannot tell you where the memory leak is. And what we can do is, in a core dump that contains all a snapshot of the current memory that includes the internal bookkeeping of the malloc implementation. And we can use that to get a list of all allocations. And then we can get a list of all the allocations that are unreachable, that don't have any pointers pointing to them. And these are allocations that we know now, while our program is running, that they will become a memory leak at the end of the program. And that means we can detect some kinds of memory leaks a lot earlier. And the problem is that a malloc implementation doesn't have to keep this information around. It's not required by the standard. I mean, we as the programmers are required to keep track of allocations and free them. But because a malloc implementation is optimized for recycling the memory that we free, it will do some bookkeeping, so it knows when we free memory how big the allocation was, because otherwise it cannot reuse the allocation because we don't pass that number into free. And I did this analysis for the GNU C library, and there is enough metadata to recover all allocations, to recover the size of the allocations, and if the malloc metadata has been corrupted, we can also detect the corruption. And so if you don't use the default memory allocator, then you need to redo this analysis for like the gmalloc implementation or tcmalloc or others, but they all have the same design pressure because they need to recycle memory that is returned by free. They will keep information that can tell them the size of an allocation, and we can do this with all major malloc implementations. If you run your program in a debugger, or you look at a core dump, you can get a list of all allocations, and you can get a list of unreachable allocations. We just haven't written the tools, but it's technically possible. And in particular, if I have an unreachable allocation and a check that tells me whether I have an unreachable allocation, I can use a time travel debugger and travel back in time to the first point in time the allocation becomes unreachable. That will usually be the time the last pointer gets overwritten. So this is the line that causes the memory leak. And currently we don't have tooling that can jump to the point that the memory should have been freed. And I think this is possible. And I don't have a working prototype for that yet. I'm still integrating my analysis into time travel debuggers. But I already have both parts. I mean, we have working time travel debuggers, including open source ones, and we have working heap analysis. I have not written the only implementation of that. Exploit developers have had these tools for years. Exploit developers have written parsers for heap corruption and parsers for heap structures. And we just need to put all the tools together. So we have a lot more tooling for, or a lot more innovative tooling for people that find security holes. And this hasn't really worked its way back into tooling for developers. And so exploit developers have also run code in emulation, in debuggers. And I think there's a lot of untapped potential for better tooling for debuggers. And I also have a demo. Of a leaky program. And so this is a program that makes naked new and delete. And it leaks memory because it doesn't free its allocations here. And the class itself will free memory in its destructor. And I had to come up with a unnecessarily complicated example to make sure that I have a memory leak that will be caught by a conservative garbage collector. So a conservative garbage collector doesn't have to find a memory leak. So there could be a pointer to the memory still being on the stack. It's not in use, but but the conservative detector doesn't do it. So what this program does is it allocates a lot of memory and it frees some but not all allocations, and I go through the core dump and I find memory leaks and I can classify them into direct memory leaks and indirect memory leaks. The indirect leaks are those that are still reachable from other leaked memory. And like the other analysis that goes through C++ objects, this kind of tool has been possible for the last 20 years, but no one has bothered to write them. And that's why I decided to give this talk, even though these are all research prototypes. I want better debugging tools. I want everyone to have better ideas for debugging tools and to do as much as possible, because debugging is such an unpleasant and time-consuming work that it is worthwhile to invest into more powerful debugging tools and to think about the problems that you would like to have solved for you and not just think what currently works out of the box. And I went too fast through my slides. Thank you very much. Are there questions?
Some questions?
This was really good talk. I got a question about one of the examples you had in the beginning about inserting into a vector which invalidates iterator.
Yes.
So yeah, GDB will not find this for you, but there is a, I think it's a glib CXX flag, a glib debug one, which allows you to wrap iterators into into safe versions, and that will find this at runtime, I guess.
So the GNU C library and so lib C++ and lib standard C++ have a way to add checks to harden the implementation that is binary compatible with existing code. And the GCC implementation also has an additional debugging mode where the iterators are not binary compatible. And this is also what the Microsoft implementation does. And so there you have iterators that carry more information and that can diagnose these problems. And the problem is that you do not have this in release builds. And if it is a problem that happens at a customer and you don't know yet how to reproduce this, then this doesn't help you. Of course, if you have proper testing, then you never run in these problems in the first place. But if you have an old legacy code base, then you can build your program in debug mode and with these checks enabled, and it doesn't find them because the bugs are path dependent. You need to run with a complicated customer project to trigger the bugs, and you don't know the trigger. So the hard to debug cases only happen with release builds. And the methods I showed where I say, well, you need to find the debug, the begin method and the end method. These methods will be optimized away. They will be inlined in a release build. But the difference between local variables that are optimized away in a release build, you can't get them back. Functions that are optimized away, we can get them back. So I can say, here is an unoptimized build, and it has all the functions that you need. I mean, I said my point of view is code is a library of functions. So current debuggers don't do that, but so if you run an optimized build of GCC and you want to say, show me the second element of the vector, it says, well, the array access operator has been inlined. I can't call that for you, but we can say, and here's a binary that has this function. Please use this one. And I have implemented that because like this entire tool is for working on enterprise code that has been shipped to the customer and that should help diagnose hard to debug problems. And yeah, I mean, use all the other tools that you have, but it still leaves some gaps where I think this fits in.
Thank you. Can I have one more? So what do you think about using Valgrind for memory leaks on release code?
So Valgrind is surprisingly effective, given that on paper it shouldn't be able to help you at all. So Valgrind, as well as address sanitizer, when used for leak detection, it tells you have a leak and it tells you where the memory was allocated. It cannot tell you where the memory should have been freed. And the usual workflow is you have a function that overrides a pointer with newly allocated memory. And this is how the information you get from Valgrind that tells you where the memory was allocated, and then you do a code review. And you find that actually, yeah, the newly allocated memory is overwriting the pointer to the leaked memory. But Valgrind can tell you have a memory leak, and it cannot tell you where the memory was leaked. And if you are a beginner, then your first instinct is, okay, yeah, the problem is in the Valgrind report, but that is where the memory is allocated, which could be perfectly fine. And I mean, I use Valgrind to diagnose memory leaks so far. It's the best tool we have without the stuff that I'm currently working on. But I think it will be much more comfortable if I can use a time travel debugger and it tells me here is where your memory is leaked.
Makes sense. Thank you.
Do you have more questions?
Okay, thanks for the talk. I have a question related to the first part, when you extract the begin and end iterators. Yes. As far as I understand it, you rely on the fact that those iterators should be mostly valid. But what in case something overrides the heap? Let's say, as you've shown, we have a vector of vector, vector of list, or even more deeply nested data structure, and something smashes the insides. Yes. What then?
So I start with the assumption that the program is bug-free, which is a bold assumption in a debugger. And I start with the global variables and the local variables. And so I have a local variable that is a vector. And then I run begin and end and dereference those iterators. And Or a better example, it's really easy to create a bad container if you use stat_span and you create a subspan out of range. You get a span with size -1 converted to unsigned. And I follow everything in this container, and then eventually I discover that this container is going to give me an object at an invalid memory location. And then I say, okay, I treat this entire container as invalid and flag it. And this might be several layers deep, so I don't know if this container itself is broken or the container that provided this element was broken and that's why it is. But because in the forward path, I go step by step through containers and contained elements, I also have a clear chain of reasoning how I discovered that object, and then I can manually review whether I think I'm looking at an object that was corrupted or this is a secondary effect because something else was corrupted first. And this is what I want to do. I'm looking at a core dump. I know something is broken and I want to find as much information as possible to look at the cause.
Okay, thank you.
Thank you, and we will take the last question.
Hi, thanks for the talk. I wanted to ask, have you considered usability aspects, for instance, integration with GDB? Because like this is kind of like a go-to tool if you have a binary and a core dump, and it would be, I think, super convenient if you could, for instance, just take a look at the backtrace and just go back and forth and just kind of like going through the functions, it would tell you, hey, by the way, did you notice that this iterator that you're using in this loop, in this function, is actually invalid, right? And this would be like an excellent hint for discovering these kind of problems, why the program went south.
Yes, so I've thought about usability. So I actually think I want this to show up in IDEs like Visual Studio Code. And the problem with GDB is that GDB allows you to write plugins, and you have access to program memory, but you don't have fast access to program memory. GDB owns the process, and if I want to do this analysis, if I want to check all memory with cross-referencing, then I also need unfettered access to the program. So what I need to do is make my program be a GDB server, so that so that you can use GDB in the same way you can use GDB with a time travel debugger or GDB with Valgrind. I can't run inside GDB, but I can make existing debuggers a front end for my analysis. And so my program will be the one that is debugging the process, and then GDB is how you access my program. Or I'll also make it an MCP server, So your LLM can do this for you. And but yeah, so I'm doing this so people can debug things they couldn't before, and they won't do that if the tools are hard to use. And we have these tools, they are not used because they are hard to use. So usability is important and ongoing work.
Okay, thank you. Just one food for thought. Maybe it would be actually reasonable to have a preprocessor that kind of like runs it at the beginning, and then just inside the GDB, you would actually already have the results, and it would be more like a lookup table because there is also an option to do an on init operations. So just a thought. Yeah, thanks.
Okay. Thank you very much. Thank you, Henning. Big round of applause once again for our speaker.